outlines of my talk is first I will show you our research footprints, what we have been doing and where we are located as an industry. Uh, uh, I will also give you some detail of where the cement has been placed, oil and gas well construction, and we'll show you what kind of problem we are facing. Then I will also come across of some of the new material design that we have developed, and we are tackling some of the current challenges. I will give you some background on molecular machine, which is nothing but a polyrotaxane based stimuli responsive polymers. Thereafter, material synthesis and the formulation of polyrotaxanes with the cement, and we'll also demonstrate the mechanical properties that we achieved or we demonstrated, and at the end the take message from this research studies. So let me show you who we are basically. So we are a oil and gas industry based company. We are the world largest oil and gas company in the world. It's Saudi Aramco. So we have several research centers around the world. So the 3 research centers in North America, Boston, Detroit, and Houston, located in the Houston Center. We also have the research centers in the Europe, like in Aberdeen in UK, Delft in Netherlands, France, that is in Paris. And then we have research center in Moscow, Russia, Beijing in China, South Korea, which is located in the Daejeon, and our mother R&D lab, which is in the Saudi Arabia, which is Dhahran, basically. So we have been working in a 7 different research area, which is mainly related to the energy related materials development, or tackling the sustainable society, or developing a sustainable society, or tackling the carbon captures and all, or several kind of areas that we have been working on. So I'm basically located in the Houston Research Center, as you can see here. Why we want to work on stimuli responsive polymers? We want to make sure that the cement that we placed for the oil well construction should last longer, basically. And that's why we thought that it is a better idea to put some different kind of polymers which can sustain or distribute the stresses throughout the cement matrix and increase the lifespan of the oil well. So as you can see here in this cartoon, we have this is a typical oil well, where we have the casing, which is a metal, hollow metal. Then we have a cement which is placed between casing and the formation, which is nothing but a earth crust. Okay, so what is happening is, when we go from surface to down at the bottom, the formation pressure is very high. Basically it ranges from atmospheric pressure to 35,000 psi. Okay, and the temperature is also very high, basically more than 200 degrees Celsius sometimes. So we need to make sure that the materials that we put downhole, basically maybe 2,000, 3,000 meter from the surface, it can sustain the such condition, basically. So what is happening in the casing, this is the production zone. When you have the oil and gas is coming through the casing, basically. So what is happening, there is a pressure difference between formation and inside the casing, and that's generate the uneven stress onto the cement matrix, and those uneven stresses basically fracture the cement. And if we have the fractured cement in an oil well, what is happening? It's a serious problem, basically. If we have the fractured cements, that means we are compromising the safety. It reduces down the production of oil and gas, and eventually it will reduce the lifespan of the oil well. So to tackle those kind of problems, the best idea is to make sure that whatever the stress which is generated because of this pressure difference should be uniformly distributed throughout the matrix of the cement. And that is the key part to make sure that there is a minimum formation of or propagation of the micro cracks. So generally in a currently what we do, we generally use the latex like a rubber based particles or some polymeric materials which shows some elastic properties. We do put those into the cements to make sure that it has some flexibility and it can distribute the stresses uniformly. However, the main disadvantages associated with the current system, which is the latex or the polymeric materials, is the long-term stability basically. So in a long term, it loses the effectiveness of the distribution of stresses, mainly because there is a degradation or the movement of the chains are restricted. So that's why we thought that how about if we put some novel polymeric materials which is based on polyrotaxane and which is governed by the pulley effect, and I will explain some of the details of the pulley effects, which can substantially lower the tension exerted onto the cement matrix, and thus it can distribute the stresses uniformly at a sub-nanometer level, so that we can have minimum cracks or fractures, and we can eventually extend the lifespan of the well. So let me show you how the polyrotaxane is different than the conventional polymeric materials, which is nothing but a difference is chemical bonds versus mechanical bonds. So in traditional polymers, as you can see here, chemical bonds is like, for example, in polymeric materials, we have the crosslinks, which is covalently linked crosslinks. Okay, so when we applied the stresses onto this network polymeric materials, what is happening is the stresses are concentrating onto the shorter chain, and eventually, if we have a repeated cycle of stresses, the shorter chain actually disintegrate, and that's why we have broken bonds or broken covalent bonds, and which once we have the broken or disintegrated polymers, it loses the effectiveness of distributing stresses within the matrix. So what we thought that how about putting the at the place of crosslinks, how about putting the pulleys basically. So pulley principle is very elegant, you know. Like for example, if you want to lift an object with your bare hand, it will take larger energy than lifting the same object with the pulleys. Think about if we put several pulleys to lift the same object, that means we are actually basically minimizing the energy or force required to lift that object. So it can distribute the stresses throughout the matrix without making too much effort basically. So this is the mechanical bonds. Mechanical bond is nothing but it's a polymeric materials which is also a covalent bond, but at the crosslinks we put the cyclic molecules like a pulley kind of molecules which can facilitate the movement or sliding of the polymer chains within the matrix. As you can see in this figure, if we stretch this polymer, we can effectively distribute the stresses in the polymer chains through the pulley effect, and that's why there is a very low chances of breaking down the polymer chain or concentration of the stress at one particular points in the polymeric networks. So before going into detail of how we synthesize these materials and how we blend it into cements and measurement of properties, I would like to take you to the history how this polyrotaxane or molecular machine has been developed. So origin of molecular machine was started in 1987. And these three persons, like Professor Patterson, Jean Marie, and Donald Cramp, they received and shared the Nobel Prize in 1987 for their works on development and use of molecules with structure-specific interaction. So these are the molecules that these scientists developed. The crown ethers developed by Pedersen, which is basically a serendipitous discovery. Since each oxygen atoms are pointing out of the planes, it's resemble the shapes of the crown, and that's why they called the polyether, cyclic polyether as a crown ethers. Professor Lane developed the krypton, and Cram developed the host gas interaction. So for these excellent works, they received a Nobel Prize in 1987 for especially host gas chemistry. Exactly after 30 years, the Nobel Prize has been awarded for the development of molecular machines. And these three gentlemen, French, Scottish, and Dutch, Jean-Pierre Savage, Fraser Stoddard, and Bernard Feringa, they received a Nobel Prize in chemistry for their contribution in the design and synthesis of molecular machines in 2016. So what they developed, Professor Savage developed catenin, which is a interlocked molecules. Professor Fraser Stoddard developed Rheology, which is a mechanical bonds, and Bernard Feringa actually established the continuous motion of the molecular motors in a cycle to get the energy or to have the better applications. So my talk is mainly focused on this mechanical bond, which is a Rheology polymers, which is basically stimuli responsive polymers. When we apply the stasis, there is a changes in the sub-nanometer structure, and it provides a kind of a different properties. So my whole talk is based on Rheology. So let's see how did we synthesize this materials. We use the monomers or components. I called them rings and strings basically. So rings components are alpha cyclodextrin, beta cyclodextrin, and gamma cyclodextrin. These are very smart molecules. You know, we have the cavity size difference based on alpha, beta, and gamma. As we go from alpha to gamma, we have size of 0.5 nanometer to 0.75 nanometer. The torus, that is the height of the cyclodextrin, is about 0.8 nanometers. The interesting properties of this kind of materials is the inner cavity is less hydrophilic than the outer cavity. So that's why we can actually insert polymeric chains within these ring structures. The strings that we use, that is the linear polymer materials, we use the polyethylene glycols, polypropylene glycols, polysiloxanes, which are linear molecules. We can also use the branch polymers to make the Polyrotaxanes polymeric materials. So those are the two components. Mainly we use cyclic molecules and linear molecules to make the initial Polyrotaxane structures. So how does it we can make this Polyrotaxane? So Polyrotaxane is nothing. It's a molecular structures where the cyclic molecules are threaded onto linear polymer chains, and it forms the mechanical bonds. And the other thing is the cyclic molecules can slide as well as rotate on axial chains. So these are, as you can see, this is the green string is a polyethylene glycol, cyclic molecules is a alpha cyclodextrin here, and we also use the capping agent, which is a nitrogen aromatic compounds. So how we can make it is a very simple process. Basically, if we mix polyethylene glycols and alpha cyclodextrin in a water, it's immediately form the host guest compounds. Basically, the cyclodextrin rings start threading onto the linear chain, and once we got this threaded cyclic molecules onto the linear polymer chain, we capped from the both sides so that the cyclic molecules cannot come out or cannot escape from this necklace like structures. So this is called the Polyrotaxane, where we can have the rotation of these cyclic molecules as well as the sliding of the cyclic molecules. However, one point we need to make sure that this, as such Polyrotaxane, it's inactive. The reason behind it is because each cyclodextrin, the cyclic molecules, the outer side is the highly hydroxylated compounds, right? So what is happening once we synthesize these materials, it's actually forming the hydrogen bonding between each polyrotaxane, and that's why there is a no movement of the cyclic molecules, and neither sliding, neither or nor rotating. So that's why it is very important to make it functional or make it movable. We need to functionalize these cyclic molecules with some other functionality so that the movement or sliding will be easy. So what we did some of the hydroxyl group, we did functionalize some of the hydroxyl group with hydroxypropylated functionalities. As you can see here, we changed some of the hydroxyl groups with hydroxypropylated propylated functionality. And once we have this functionality, what we did, we linked these polyrotaxane molecules with high molecular weight polymers. Here we use the polyacrylic acid so that this polyrotaxane is blended within the polyacrylic acid. So as you can see in these structures, if you imagine, if you pull these polymers from the top and the down, what we will see? We see the motion or sliding of the cyclic molecules onto the linear chain, and it cannot you can have a maximum strain with minimum effort or minimum stress, and it can also distribute the stresses within the polymeric matrix. So what kind of property difference we can get from such kind of polyrotaxane polymers? So this is a traditional or a fingerprint region of stress strain curves for pretty much all polymeric materials, where we have the non-linear softening, which is a R-shaped behavior, where we can have the particular or defined yield point. We can also have the non-linear stiffening behavior, which is as you can see, with a minimum amount of stress you can have a maximum amount of strain. And we can also have the materials like a linear elastic, which is a rubber, where we have a stress is equal to strain basically. So non-linear stiffening behavior actually we can observe in artillery wall or spider silk. And for non-linear softening behavior we can have the thermoplastics, some thermosetting also. And linear elastic is a rubber like polybutadiene or any natural rubbers. So how our polyrotaxane is different from the traditional polymers? As you can see here, this is the traditional polymers stress strain curves, and this is the polyrotaxane's stress strain curve. What is the difference? We have a two zone basically, 1 to 2 and 2 to 3. So in 1 to 2, it behaves like a non-linear softening behavior, and 2 to 3 it behaves like a non-linear stiffening behavior. So basically in polyrotaxane we are achieving both kind of properties, non-linear softening and non-linear stiffening. At the same time, when we applied the stress in traditional polymers, with a higher amount of stress you can get some strain, but with the same amount of stress, as you can see with polyrotaxane, you can get X-fold strain. So basically we can have lots of strain with a minimum effort. How it will work within the cement matrix? So we are calling them sustainable cement's mechanical properties. So in this cartoon, as you can see, which is an illustration of how or the postulate how it can work basically. So in the background it's a cement particles, and we mix this polyrotaxane into this in the cement materials. When we applied the stress, generally when we experience the stresses, generally these polymers can distribute the stresses so that there is no cracks. But even if there is a cracks, what will happen? Because of the there is a repulsion between the cyclodextrin ring, it can actually recover and heal the cement particle. So basically the cross links which comprise of cyclic molecules which equalizes the stresses because of pulley effects and the sliding motions of the molecular moieties, which actually allows the cement particles to coalesce and not able to disintegrate from the structures. So let me show you some of the experimental results that we have. As you can see, cement slurry formulation, we prepared the control and the cement with PR, which is a polyrotaxane. So these are the components we use: the cements, silica, and polyrotaxanes. We use these three kind of different additives, which is mainly used for rheology controls, like for example, ensure there is no loss or no water separation from the cement matrix. So we are using about 1% of polyrotaxane into cements. All other components are the same in both the formulation. I see how 1% of polyrotaxanes provide what kind of properties it can provide. So these are the typical rheology fluid loss and thickening times that we measure for the cementing materials, which basically is showing that even if we add the polyrotaxane, we are not seeing that much difference in the typical cement formulations. And as you can see, the plastic viscosity yield points. Plastic viscosity is basically gives the information about how the pumpability of the cement downhole. Yield point is very important because the cement is a high density material, so you need to make sure that you have uniform density throughout the cement matrix. So higher the yield point, better the uniformity of the density. And we also have the fluid loss properties, which is control and polyrotaxane cements, which is telling us about how the water is entrapped within the cement formulation throughout the curing process. And here on the right side, you can see the two plot of control and polyrotaxane, which is basically telling in the control is about at 5 after 5 hours cement start curing, and in polyrotaxane cement mixture, which is start curing at about 5:45 hours basically. So so this can be the curing times can be tailor made based on different additives which is available in the market. So basically we can use the retarder to make sure that we can delay the curing process. So so that is the transition time of the cement slurry. So most important things that we were focusing is the mechanical properties basically. So what we eventually want to achieve is the better mechanical properties while we adding the polyrotaxane into the cement matrix. So here you can see we made the cylindrical sample of the cement and we measured the mechanical properties using this condition. Like for example, we have a confined pressure of 3000 psi onto the cement, and we also have the cyclic stress for the Young's modulus measurement, and we have a uniform uniaxial stress for the compressive strength. And the measurement was done at 300 Fahrenheit, which is basically 150 degrees Celsius, and under confined pressure of 3000 psi. So when we applied the axial stress, the axial stress goes up to about 6000 7000 psi. So overall pressure into the chamber where these samples was placed is about more than 10,000 psi at 150 degrees. So those are the conditions we are looking for. Those are the conditions we want to make sure that our materials can withstand. So as you can see, this is the neat cements without any polyrotaxanes. So when we applied the stress, what is happening? It's shattered into the pieces after certain compressive stress. While in the case of in these pictures, while in the case of one weight percent, just 1 weight percent of polyrotaxane, we can able to reduce down its volume about 30% or 27% basically, without disintegrating the cement, which is a highly brittle material, you know. So it proves that if we able to distribute the stresses within the cement uniformly, basically you can preserve your cement samples under such a high extreme condition at 150 degrees Celsius and overall pressure more than 10,000 psi. So let's see the numbers, how the numbers of this mechanical properties looks like. So the compressive strength, as you can see here, the neat cement compressive strength is about at room temperature about 6000 psi, at higher temperature about 7,000 psi. With cement with polyrotaxane, we have a little bit higher compressive strength at room temperature as well as 150 degrees Celsius. So, which is also a very unusual. Generally, when we add the polymer materials or other polymers, what is happening? Polymers for latex generally introduce the flexibility, and that's why it should give the less compressive strength. But here we are doing complete different scenario. We are not compromising with the compressive strength of the cement, although we are putting some polymeric materials, which is polyrotaxanes. The other thing which catch our attention is the Young's modulus. The Young's modulus of neat cement is ranging from 11 to 12 gigapascal, and it reduced to about 8 to 7 gigapascal for cement with 1 weight% polyrotaxane. So what it generally suggests? It suggests that we are not compromising compressive strength. At the same time, we are able to reduce down the Young's modulus. So basically, we are introducing the toughness into the cement matrix by using the polyrotaxane. So that is a very encouraging results that provides an idea that how the polyrotaxane or molecular machine type of polymeric additives actually distribute the stresses within the cement matrix and provides such a fantastic mechanical properties for the oil well cements, which can actually help in extending the lifespan of the oil and gas wells. So at the end, the take-home message is that we introduced the 4.0 IR. In industry, we generally says 4.0 IR, which is a fourth generation industrial revolution technology. We introduced a novel chemistry, which is already established, but we are finding the applied research area of such kind of materials. We call them rotaxanes and mechanical bonds. Owing to the polymeric poly types of crosslinks, actually, we can effectively redistribute the stresses exerted onto the cement matrix, and it helps in restricting the formation of micro cracks and fractures within the cements, and which can help in solving several issues. We can also I have also demonstrated the effect of polyrotaxane, just 1 weight%. It actually transforms bitter cement into the tough cement without compromising the compressive strength. Compressive strength is also very important. We have to have some kind of compressive strength within the cement. Basically, for oil and gas application, the cement compressive strength should be more than 5,000 psi. So we are above 5,000 psi, but at the same time we can able to reduce down the Young's modulus, basically introducing the elastic behavior. So generally, what will happen if there is a cracks in a already producing well? What we do, we generally seal those cracks, and we need to go. The resin should travel through from surface to the thousands meters down the hole. So that's why we are the industry all over the world. Industry spending huge amount of resources on remedial jobs. So we can reduce down the cost associated with those remedial jobs, and basically we can improve the longevity of the oil and gas well by blending just 1 weight% of polyrotaxane into the cement matrix. I would like to acknowledge some of the people here, our team lead Carl Temlitz, Peter Bull, our laboratory staff, Roland Martinez and Kenneth Johnson, Aramco America's supporting staff, as well as the management of Aramco America.